formal language and automata theory. So the objectives of learning the subject. We should have knowledge. We will have knowledge on the following. To know how a computer work. First objective here, the concepts of automata theory and theory of computation. Second, we will learn here to identify different classes of formal languages. We will see here different classes of formal languages. We will have the idea of regular languages. We will have the idea of context-free languages. We will have the idea of recursive language. We should have the knowledge of recursively enumerable language. Third part, to design grammars to accept the formal languages. In last class we had discussed the prerequisite topics to learn formal language and automata theory. We have discussed set theory. We have discussed graph and a tree. One of the major topic is called mathematical induction. We must know. Let us discuss what is mathematical induction. We have to prove that a relation is true. You can say relation or function or equation is true by using mathematical induction. Basically, there are two proof states. Step 1 or proof step 1 proof by basis. Step 2 proof by inductive hypothesis. What inductive hypothesis say that? It implies that this statement T of n is true if and only if you can write here this statement T of n minus 1 is true if T of n is true. So that is implies that T of n minus 1 implies T of n. Let us take one example, saying the mathematical induction proof. Mathematical induction proof. So let us take a declarative statement. You can write here example. Prove that one plus 2 plus up to n is equal to n into n plus 1 divided by 2. We can best use mathematical induction method to prove LHS equal to RHS. So the mathematical induction proof derives in two steps. Proof by basis. So we have to prove LHS equal to RHS. Proof by basis, which is called trivial case. When n equal to 1, then LHS equal to 1, only one term will be there, and RHS equal to 1 into 1 plus 1 divided by 2 is equal to 1. Proved. LHS equal to RHS. as I already told, mathematical induction derives in two steps, then proof by inductive hypothesis. Proof by inductive hypothesis. What do you have to prove that? We have to prove that the above equation or relation is hold good for n minus 1 terms also. So let us prove. What we have to do? Substitute n minus 1 in place of n in RHS. And LHS. So LHS equal to 1 plus 2 up to n minus 1 terms, up to n minus 1 terms. Now what is RHS? RHS equal to, so what we have to do that? Substitute n minus 1 in place of n. So what is RHS here? N wherever n is there, n minus 1 into n minus 1 plus 1 divided by 2, that is equal to n into n minus 1. It is better to write like this, or 2, or even if you can write here n minus 1 into n divided by 2. So LHS equal to RHS is agreed upon the declarative statement. Hence, it is proved that the statement is true. Symbolic notation in learning formal language and finite automata. So we was discussing language, or which we call the formal language. A language is defined as a set of strings of symbols drawn from a finite set called alphabet. So this we have already learned. So what we are trying to explain that sigma star, sigma plus are also are languages derived from alphabet sigma. So what is sigma star? If you see that sigma star is nothing but epsilon 0 1 0 1 1 0, any such combination of 0 and 1, any such combination of 0 1. So what did it include? Here sigma star include an element null called epsilon also. Similarly, let us discuss about one more derived language where all the string over 0 and 1 but here sigma plus exclude the element or string null or null. Which we are finding here, it is not there in this one. This is also required for us. Brief introduction to finite automata. Finite automata. If you are going to the BPUT syllabus, you will be finding the introduction to finite automata in module 1. What it cover? It cover what is alphabet, what is string, and languages, which you call the formal languages. This portion we have already discussed in my previous video. You can see the previous video to understand alphabet, string, and languages. Today's topic will give formal definition of automata, finite automata, formal definition of finite automata. A finite automata we can say better because we are defining one a single machine, finite automaton. can be defined in 5 tuple. Machine M, capital Q, set of states, input alphabet, it is alphabet, transition rule, initial state, set of final state. The complete definition we were going to give about the formal definition of the finite automata. So we are going to give a brief introduction to this one. So here we will basically focus about the transition rules. If you are in a state, consume input symbol, consume an input symbol, you will go to another state. We will give more definition, complete definition in next class. If you are going to give the description of finite automata is a simple mathematical model of a computer that takes input, processes it, and produce output in the form of accepting the formal language. So this seeing an input tape, and let we have a string here with end marker on the tape, some of the end markers on the tape, and this is your input string. And there will be finite control, which is reading input, this is the mathematical model of the computer. The very next is that we will learn state transition diagram, which is also called transition system. An example I will show you. Suppose here we have a two state taken from the graph concept. Two concentric circle for the final state and single circle for a initial state or start state. We are going to accept even number. All binary even numbers. So we all of you know that if you consume 1, it will go to odd state. Consume 0, it will go to the even state. If you are in the q odd state, on consuming 0, it will go to the q even state. From q even state, if you are consuming 1, you will go to the q odd state. This is the state transition diagram. Then we will also learn transition table. So what is the transition table here? If you see one thing, how many states we have here? Q odd, Q even, and what is input symbol? 0 and 1. If you are in the Q odd and whichever the final state, put in a circle, and with the starting state, put in a arrow mark. Q odd getting 0, Q even, Q odd getting 1, Q odd, Q even getting 0, Q even getting 1, Q odd. Next we'll learn DFA, which is called deterministic finite automaton, or we call DFA. If we will see first formal definition, then we will discuss what we are going to discuss here. Description of DFA. It is as like a finite automata. We will write. We will be focusing basically on the transition rules, and in description of the DFA we will see no input causes control to move more than one state. Or we can say that a state does not contain more than one move for the same input symbol. Also, we should also know that each and every state has to consume all the input symbols present in alphabet. We will give more details of DFA in my next class. Next is that NFA, non-deterministic finite automata. So what is speak about that? We will also here we will discuss the formal definition. Here we'll most focus on mapping function, that is 2 to the power q. Will give more details of that one. They will give the description of NFA. Next we will see the acceptance of NFA. If any completed path ends with final state, then the language is accepted the details we will see how it is work. And the DFA transition table, transition diagram, and transition tables, NFA transition diagram, and transition table, then we will learn equivalence, equivalence of DFA and NFA. Here we will see that DFA a DFA can simulate a NFA, and the very next we will see algorithm to convert NFA to DFA, and the very next topic we are going to discuss. So these are the major topics we will discuss. The very next is that next topic we are going to cover here, minimization of DFA, and my hill Nerode theorem.